So, yesterday we went up to the Gaussian or normal PDF. So, today we will look at a few more examples. I use number 4 for Gaussian, right, that is what I have here. So, okay, so number 5. So, is there any Gaussian PDF is okay, right? You understand there is nothing much else to say about it. Just remember the role of m and sigma. What is the role of m? It shifts it from left to right. If m is positive, where does it go? It goes to the right. If m is negative, it goes to the left. What goes to the left? The peak, and the maximum of the PDF occurs at m, and also the PDF is symmetric about m. So, these things you have to mentally keep in mind. Okay? Okay. Then now this turns out this is very this PDF is highly related or very closely related to the Gaussian PDF, right. Okay, there is something else I have to say. So, this is defined only for positive values with the argument or non-negative values with the argument. So, whenever some such thing like this comes, it automatically means what? The PDF is 0 for x less than 0. Okay. So, if you plot this, what does it look like? It looks like this. Note that there is an x up here, it is a crucial x. Why is that x so crucial? It turns out that the presence of this x makes integration of this PDF, that is finding the CDF, enables the finding of the CDF, right. And so the CDF is immediately written down. What is the CDF? Is integral from 0 to x of some, you put some dummy variable here. So, if you do that, what do you get? You recall how to integrate by parts. I hope it is not a big problem, or not even integrate by parts. I mean, I am assuming that you're right, you can easily write this. It's 1 minus x of what? What is it? What will come here? Minus x squared, the same as this, minus x squared by 2 sigma squared. So, this of course again for x greater than 0, and obviously, right, f of x is 0 for, you have to say this if you want. Now, there is one item I skipped over, which is what? Can we write a capital F of x for the Gaussian PDF in closed form? Answer is no. Note. It is not possible in closed form. I should have said this before I started that, but I think it's good to remind ourselves, right, when we can we can't, all I am trying to say is we cannot take the closed form expressions for CDF always for granted, which is another reason why PDFs are mathematically more convenient to manipulate than CDFs. Something as important as a Gaussian PDF, right, you have a closed form expression only for the PDF, but not for the CDF. But does that mean that capital F of x does not exist? Absolutely not, right. It has to be a number between 0 and 1. It is just that there is no nice expression for it, that is all. So, later on we will see some upper bounds and approximations and so on for the Gaussian PDF, which have been used to either approximate or bound. Anyway, so we will come back to this issue after once we go through some of these examples, right. But I have to emphasize this. Okay. Then let us look at an example. We have already seen the Cauchy, right. So, I think the Cauchy example or okay, let me just for sake of completeness also give it a name. Maybe I did not call it the Cauchy PDF is basically the 1 by, we saw this already. So, let me actually put an alpha here. Alpha by, I will write it as alpha by pi into alpha squared plus x squared rather than 1 by, right, and this is for all x. So, this we have already seen, right, as an example of a two-sided PDF long back, or not last week, right, when we started talking about PDFs, and we know that the CDF is what? This is in some sense my very first example. This is the classical earlier I may not have introduced the alpha, but you can clearly have the alpha also, and obviously this alpha has to be greater than, has to be a positive parameter, it cannot be a negative parameter. Earlier I believe I may have taken the alpha to be unity, right, the previous encounter with this. So, this is again true for, I do not have to say anything, when if I do not qualify this, this is understood, right, x is any real number. So, here we have, okay, so there is some similarity between the Gaussian CDF and this CDF, in that both of them do something like this. And it turns out that no matter what value of alpha you pick, right, the value of this capital F of x is exactly 0.5 where at alpha equal at x equal to 0, isn't it? Similarly, if you take the Gaussian PDF and set m equal to 0, you always get capital F of 0 to be half, because PDF is perfectly symmetric about the origin. Similarly, this PDF is also symmetric about the origin, and the Cauchy, the Laplacian PDF, the two-sided exponential that we wrote, was also symmetric about the origin. But what is the fundamental difference between, right, okay, there are some similarities, but there is a big difference between Cauchy and Gaussian or normal. The difference has to do with how the tail of the PDF decays to 0. The Gaussian PDF decays as e power minus x squared, which is very fast, whereas what is the rate of decay here? It is just barely sufficient to be integrable. If I had something like 1 by x, I would not, let us say not counting, or 1 by 1 plus x or something, let us say you can, if you want to construct a PDF like that, what is the immediate problem you run into? So let us say you want to go all the way to infinity. It will not be integrable, it will not have finite integral, right, it will not have finite area. So, this x squared is almost like the smallest power of x in the denominator that is required for having a finite area. So, as a consequence of this x squared, we will see later on that this Cauchy PDF has no moments, right, we are going to see that, has not even the first moment if you look at the careful definition of the first moment, right, whereas the Gaussian PDF has every single moment you can, right. Okay, so that is for later. So, this PDF is, right, is called a heavy tail PDF, is an example of a heavy tail PDF, right, it's a rate of decay decays as 1 by yep. Okay, so all these PDFs have some mathematical property that we should be looking at. One more interesting example, I promise not to go any further than this, is the so called ArcSine PDF. You might wonder where this thing might occur. We will actually derive this find an example, a real life example of where this can in fact occur, say mod x less than 1. What is interesting about this? Why is it, first of all, does it have finite area? Does it? Does it have a closed form CDF? What is f of x? Again you have, exactly, somebody said sine inverse. It's exactly like this, except that the tan inverse becomes a sine inverse. So we will write these inverse trigonometric functions with just the minus 1 superscript, right, instead of arc sine and arc tan and so on. So arc sine or sine inverse of just x, and this expression is valid only for minus 1 less than x, you can say even equal to. What is the value at minus 1? It turns out it will be 0. So what is this? Just sketch these things. So this as a sketch will look like what? Is the PDF bounded? Answer is no, it is not bounded. PDF can go up to infinity at x equal to minus 1 and plus 1, but that does not prevent it from being integrable, having finite area, right. So this thing looks like this. And as a consequence of this going to infinity plus infinity here and here, what does this capital F look like? It will take off, it will go up to, right, go up to minus 1. This is the portion where it's 0. So if I want to fully specify this, I have to say f of x is this between minus 1 and 1, f of x is 0 for x less than minus 1, and f of x is 1 or blah blah blah. I am not going to write all that stuff here, I do not think it is needed. We will just plot it. What is the slope at minus 1? It takes off vertically and then does this. Ends at plus 1 also, it ends vertically. So in this portion from z, okay, so this value is unity. Again, as usual, as with all these, right, the symmetry about the origin says what? That the value at 0 is 0.5. If I put x equal to 0, note this is sine inverse x here. So if I put x equal to 0, obviously I get 0.5. So this portion corresponds to this expression. So you can right endlessly debate, does this function have a derivative at x equal to plus 1 and minus 1? As I said, we are expanding our concept of derivative to include such cases also. So there is nothing, right, peculiar about this PDF at all. It is a very healthy PDF, and it just turns out that it is unbounded at plus 1 and minus 1, that is all. Okay. So this kind of thing can never happen in a discrete distribution, right. You can never get a PMF. A PMF always has to be bounded between 0 and 1. It's impossible for a PMF to behave like this. So this is one more strong, right, what shall I say, illustration of the point that a PDF value is not a probability. Remember that for forever and ever, right, especially if you go for vivas and so on. You may be asked this question, immediately say no, right. PDF is not a probability. However, of course, CDF values, each and every one of them is a probability. So I am not going to, there are if you go and look in tables in books, there are lots of more examples like Erlang PDF and Gamma PDF and this and that. They get more and more mathematically complicated, so I am not going to do any more of them. I just wanted to give you the simpler ones, right. Most of these we will use as examples later on in the course also, so please be familiar with them. Especially the Raleigh turns out, which I just erased, has some very interesting applications in wireless communications, right. So what is the connection? Let me just say one small thing before going ahead with the, so connection to histograms or probabilities, well, right. The PDF connection, let me say the density function is connected to histograms in the sense, connection in the sense there is a relation between a PDF value and a histogram. So supposing you consider an interval, it does not matter closed or open, x naught say minus delta x by 2 to x naught. So you pick some value and pick some delta x. So the width of the interval is delta x. It can, I am just taking a symmetric interval for convenience, I could take it non-symmetric also. So what is the, so the probability of finding of encounter or getting this interval is basically probability of this interval, as we said, for will be f of x naught into delta x for small delta x, right. And assume of course delta x is positive. So this, if I plot this x naught and I look at, if I run the experiment many times, what is going to be, assume that, right, at this number occur, that this interval occurs some n of x naught times, right, this interval occurs n of x naught times it occurs. So this would be a histogram that you could have drawn of the experiment. So this is a different, so I am assuming that I have carved up the x axis into small bins, right, and plotting a histogram for continuous quantity, which is very doable, which is what, right, most people do when they encounter some data. One of the things that people do when they get a lot of data of some experiment is do something like this. So this particular n of x naught, and let us say you have the total number of trials as some n. So what is the relationship now? So this f of x naught delta x is supposed to be roughly n of x naught divided by total number of trials, which we will call say so I will use capital N just to make, I do not want to use small n here, just use capital N. This is this n of x naught. So this kind of a plot, again as I said, is a histogram. So what is it saying? That the PDF value at any x naught is what? Is proportional to the histogram, to the histogram count. So this delta x will, right, if you want to remove the delta x, you have to say this is proportional to that. So there is obviously this connection, right. The PDF is not totally unconnected from probability. This is exactly, right, it models this probability of getting an observation in this interval. So given some unknown, right, say unknown distribution, how would you go about deciding which PDF is a good model? You have to fit the, you have to look at the histogram carefully and fit various PDF models to the histogram and see which one best fits the data, and that is not a trivial exercise, I have to tell you. Okay. I just say f of x naught is proportional, alpha is proportional to n of x naught. Assuming you have n, this n is fixed, right. Okay, so just keep this also in mind. This could also be, right, I am obviously not going to ask this kind of thing in the exam, but somebody could easily ask this question in a Viva or interview.